Like so many topics that we cover in Algebra 2, today is a day where we're going to talk about something that is mind-blowing. We're going to derive the formula for the sum of an infinite geometric series. Now, at first glance and at first listen, that may not sound so mind-blowing, but I want to point out that what I just said is we're going to find the sum of an infinite geometric series. Infinite. In other words, what we're going to do is we're going to figure out a way to take a sub 1 plus a sub 2 plus a sub 3 plus dot 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 all the way to infinity. And we're going to add them all up and get a total. Now, that should be pretty mind-blowing to you because if you recall, there is no end to infinity. There's no point where you just stop adding numbers. So this is a pretty mind-blowing concept. So let's talk about how it's possible. First of all, I will tell you this. If we try to do something like 1 plus 2 plus 3 plus 4 plus dot dot dot, that is not going to get us, we will not be able to calculate a sum because as we continue to move towards infinity, the sum will just get larger and larger and larger. There is no final sum. So this guy just doesn't work at all. On the other hand, it turns out that if we take a bunch of fractions like 1/2, and then we start going smaller, like 1/4, and then 1/8, and then 1/16. It turns out that if we add these up and we keep going to infinity, we can actually get a sum. Now, let's take a look and talk about a few things here that are related. For one thing, I've said that this is true for an infinite geometric series. And it turns out you cannot get a sum for an infinite arithmetic series. So it's really important it's geometric. And I want to remind you that if we have a sequence or a series that's geometric, we should be able to verify that there is an R, or a common ratio between terms. And the way we find R is we will take the second term and we'll divide by the first. So in this case, we'll take like 1/4 and we'll divide it by 1/2. And I'm writing it in this way because I want to remind you that when you divide by a fraction, you simply flip the second fraction and turn it into a multiply. And when we do that, we get 2/4, and we can reduce that down to 1/2. So what I want to point out here is that we now have an R equals 1/2. And it turns out that is a magical value that allows us to get the sum of an infinite geometric series. Why is it magical? Well, in order to calculate the sum of an infinite geometric series, we have to have an R value that is less than 1 and greater than -1. Okay, it can be negative 0.5 or negative 0.75, or it could be 0.25 or 0.75. It can be any decimal or any fraction in between -1 and 1. And if it is, then we can then compute the sum of the infinite geometric series. Now, I hope that you're still skeptical, and you deserve an explanation as to how this could possibly be. So we're going to play around a little bit here with some ideas. We're going to do this. We're going to say, what happens if, I want you to notice that in the formula, oh, by the way, I've written here, this is the formula for the sum of a regular geometric series. This is the formula for a sum of a geometric series when there is a finite number of terms, or just, a number of terms that we can count, n, right? So the formula says that we will take R and we will raise it to the power of n. Okay, well, in a finite geometric series, n will be some number. So let's go ahead and try taking our R and let's raise it to some powers. So we're going to go ahead and raise R to like, oh, by the way, if you don't mind, R is 1/2. Let's just write it as 0.5 because I want you to be able to try this on your own calculator at home. Let's go ahead and try raising 0.5 to the power of 10. And let's see what that looks like on the calculator. On the calculator, if we take 0.5 and we raise it to the power of 10, we get 0.0009. Okay, that's a pretty small number. Now, just for the heck of it, we're going to try to raise 0.5. Oops. We're going to try to raise 0.5 to the power of 100. Let's try that on your calculator. So I'm going to go ahead and hit cancel, and you're going to do 0.5 raised to the power of 100 equals. Whoa. That's a really tiny number. I don't know if you guys remember scientific notation, but what they're telling me right now is this. They're saying that that number here is equal to, gosh, what is it? It's 7 times 10 to the negative 31. Let me see if I can show you what that is. It's 7 times 10 to the negative 31. That's what the calculator was saying. And I'm going to remind you that when you have something like 10 to the negative 1, that just means 1 over 10, which means 0.1. Okay? If you have 10 to the negative 2, that means 1 over 100, or 1 over 10 squared, and that's 0.01. So when we have 10 to the negative 2, we have like 1 0. And then we have the number 1 that we're interested in. So when we have 10 to the negative 31, that means like 30 zeros. So it's I'm not even going to take the time to write all of them, but it's a lot of zeros, okay? And then finally at the end of all that, we get a 7. As far as we're concerned, that number is almost 0. And what's interesting about this is that 0.5 raised to 100 almost gets you 0. And by the way, on your calculator, it might even show up as 0. But 100 is not that big of a number. So we're going to go a little bit further. We're going to try 0.5 raised to the power of 1,000. So again, we hit the calculator. And let's cancel this and 0.5. And I want you to try it on your calculator at home. I'm going to go and do this 1, 0, 0, 0. And when I do it, I get 9 times 10 to the negative 302. On your calculator at home, I'm expecting that right now what you're seeing is 0, because most calculators cannot do 10 to the power of negative 302. The most they can do is 10 to the power of negative 99 or 10 to the power of positive 99. So I'm suspicious your calculator right now is saying 0. And that's when we have simply 0.5 raised to the power of 1,000. Now I want to remind you of something. 1,000 is not that big of a number. When you're talking about infinity, infinity is bigger than 10,000. It's bigger than 1,000,000. It's bigger than 1,000,000,000. It's bigger than 1,000,000,000,000. Okay, so just imagine that we started getting larger and larger and larger numbers that we were raising 0.5 to the power of. Okay, what I'm talking about is this guy right here, r to the power of n. If this part of this formula, if this n is getting really big, and if r is a fraction like 1/2, and by the way, when I say like, I mean 2/3 works, 3/4 works, anything that's less than 1, okay? If we take a fraction and we raise it to a really large number, we essentially get 0. We just proved it by raising 0.5 to the power of 1,000, and by imagining 0.5 raised to the power of 1,000,000 or 1,000,000,000 or 1,000,000,000,000. I want to remind you that what we're talking about here is raising whatever r is to the power of infinity. In other words, we're looking to find the sum of an infinite number of terms. This is the formula for the sum of a finite number of terms. We want to find the sum for an infinite number of terms. So that's going to make this n into infinity. And what happens when that n gets to infinity and this r is a fraction is this guy just goes away. It just becomes 0. And magically what we get is a formula that looks like this: a sub 1 over 1 minus r, bada boom, bada bing. That is our formula for the sum of an infinite geometric series. It's simple, but here's the tricky part, is that most people who just memorize the math that they're taught in school will use this formula even when it's inappropriate and therefore get the wrong answer. The only time we can use this formula is when our R value is less than 1 and greater than -1. Now, you'll be given some practice problems to try, and some of them you'll be able to compute a sum for, and some of them you won't. You need to understand this concept, and that's why I took you through all of this background in order to get this very simple formula.